Right, so welcome everyone to the afternoon session today, where we're going to have interesting connection to data analysis. So we'll start with David Berman from Queen Mary, who's going to tell us about the inverse of exact renormalization group flows as statistical inference. David, please.
Thank you. Okay, so this is a slight change in tack to the other talks on M-theory, and I'll sort of describe why people as M-theorists, as string theorists, as theoretical physicists, you can realize that there's a whole toolbox that you have which is actually relevant in statistical inference. And for those of you who don't know what statistical inference is, I'll explain. And we will get to, in the end, actually how methods that you are familiar with in things like renormalization group flows actually appear now in contemporary methods in artificial intelligence. So this talk is based on two papers. This paper, which came out I think last April, is with all three people here, and this one is just myself and Mark Klinger, who's a PhD student. Right, so what's the point? So this work was motivated really by two questions. These questions are not new, they've been hanging around for a while. So the first thing is, how do we understand renormalization group flows in terms of information theory? And the other one is, can we use ideas of theoretical physics to better understand machine learning? So as a comment on the second one, you all must have noticed that AI and machine learning has been prevalent in the press, in the numerous forms, and that there's been a whole revolution in machine learning probably since about 2014 with AlphaGo. And there has always been this frustration in machine learning that this is something that works, but we don't know why. And it's sort of the opposite side of string theory, which is beautiful and we have a lot of understanding, but it's not clear whether it's to do with reality or not. But yes, I don't really want to make too much comments like that. But so the question is, can we apply the ideas that we've got and the methods that we've got in theoretical physics to better understand machine learning, and in doing so provide methods for machine learning? So the plan for this talk is this. I'll introduce the basics of the exact renormalization group, which is, of course, different to Wilsonian. And then I'll also introduce this idea of dynamical Bayesian inference, which is the mathematical basis for how we infer what models are of nature or anything of data, given data observations. So when we talk about in this talk statistical inference or Bayesian inference, it's saying what can you infer about a model and its parameters by the data that you observe, okay? Now, the main goal is this line, which is the construction of an explicit map between renormalization and statistical learning, okay? And I'm gonna, in the talk, I think there's a whole load of technical things, which no doubt, you know, is not your interest, but I want to get the idea through the things that we are very familiar with in things like renormalization. Ideas of integrating out is essentially how we cast away information. The idea in learning and inference is how we incorporate information into a theory. So I observe data, I know more about the theory in the world, therefore the theory changes through the incorporation of that information. When I do renormalization, it goes the other way around. Because I don't know things, I sort of know less and less when I go out into the infrared. I've thrown away all the ultraviolet degrees of freedom, and it's just the theory in some sense of ignorance. And that is showing you that basically renormalization flow to the infrared is information theoretic inverse to what we do when we're doing learning. And then putting the mathematics behind that is what the challenge is. Okay. So, I mean, everyone knows this, but let's introduce some notation. The Wilsonian picture of RG describes an action functional, which is in some sense depending on scale, and we write it out like this. And then we have a bunch of parameters, lambda, and a set of terms in the Lagrangian controlled by lambda, and these are like our set of coupling constants which govern the strength and contribution of each term in this expansion with Li's. And then you can think of the lambda i's as coordinates on the space of possible actions. Of course, it's not all possible actions. You parameterize them in some way, but you want to sort of say, right, given that parameterization, then these are coordinates in that parameterization of possible actions. And then the flow is then generated this way. And so basically we have a one-parameter family of actions at each scale. Okay? And this is what we're all familiar with. Now, the probabilistic interpretation is you go to Euclidean theory, and then you should think of this thing as a probability at scale lambda. And then these things coordinatize an exponential family of probability distributions. Okay? So this is just what would be called statistical field theory, and basically then we want to look at how probability distributions and their families can change under scale. Now, and then the exact renormalization group flow is then where we have this flow under the probability distributions is governed by a functional differential equation. Okay, and the idea of ERG, one of the various properties of this, is that this is some exact non-perturbative description that's also coordinate invariant in the sense as you can change couplings and change all sorts of things and you still get this flow. Okay, so we're going to view the exact renormalization group as a diffusive flow on the space of probability distributions. Okay, so now let's switch to Bayesian inference and what the Bayesian problem is. So the Bayesian problem is I observe data and I want to know, once I've observed data, how does the parameters in my model change? As a piece of trivia, Bayes' paper is the second paper on the Inspires archive. You can take a guess at what the first one is. The first one is Newton, second is Bayes. So it's a very fundamental thing because often when we want to measure, say, the charge on the electron, we want to measure the mass of the proton, well, we don't actually measure that. We measure something in a laboratory, and then from there we infer what the probability distribution is on those parameters. Okay? So you have always some model, and then you've got parameters in the model, you make observations, and through the observations you need to use Bayes' theorem to infer what the parameters are in the model. Okay? Now, there's another thing to this, which is something that we have to sort of accept mentally, which is perhaps not what we always do, is that what Bayes' theorem gives you is not what the parameter is that you measure. It gives you a probability distribution on the parameter. Okay, so if I had, I don't know, the standard model, and I measure some scattering, then what Bayesian approach will do will give you the probability distribution over the space of the couplings. You won't actually get the couplings themselves. Okay? You have to absorb that what you're always learning is a probability distribution. Any questions about Bayes before I continue, on the grounds that Bayes is probably the least familiar for this crowd? Good. Okay. So when we do Bayes, this is the fundamental formula. P, Y is the data. U is the parameter that you want to come up with the probability distribution of. And so we often have something like a model, which says basically given parameters U in your model, then this is the probability of y happening. This is an exponential model, just as an example. And then, but what you actually want to know is what's the probability distribution of u itself, as in the parameters that you're trying to determine. And to do that, you basically use this formula, which gives you your probability determined by the model. And then you need this thing called the prior probability, which is what you approach and say, this is what I believe the probability distribution is of the parameters in my model. Often this could just be flat and you have no prior knowledge. And then what you get in the end, what the output is this thing which is what's called the posterior distribution, which basically says, after seeing data amount t, this is the probability distribution for your parameter u in your model. Okay? So this is the posterior. And as you get more and more data, as t increases, the posterior changes. Okay, so as I measure more things, then the probability distribution changes. So one of the things that we then did was treat that system as if you have, instead of just a few measurements, take a large number of measurements and then slowly increment them one by one and derive in some infinitesimal limit a dynamical equation for how our probability distribution of the parameters that we are interested in changes on the amount of data. So t is the amount of data. And then the result is that this is a first order equation governing the change in the posterior probability of of u, the parameters in your model. And the source term on the right-hand side is basically driven by something which is called the KL divergence. So the KL divergence is a measure of the distance between probability distributions. And you can think of it geometrically as the Kähler potential for the Fisher information metric. So this is the first appearance of where we start to see the beginnings of what is now called information theory. This thing D, you should think of as the Kähler potential for the information metric. And what it is, it's the distance, it is measured in some way, between the probability distribution of real data, that's Py of star, and P of y is what you've got in your current model, and then E is inferring that this is the expectation value of that distance for your current probability distribution estimate. Okay, so this is a formula which says, as I gain more information, I solve this, and this term equals 0 if my model exactly matches reality. And if it doesn't, it says how I would change my model given every piece of data that I observe. Okay? So this is a first order flow in the space of probability distributions that's essentially sourced by how far away your model is from reality. Okay? And then what you can do once you've got what probability distributions are, the probability of anything in your model is determined by this equation. Okay? And the whole point is, over time, where time is the amount of data, you gain more and more information. And you flow to what we would obviously call a fixed point when it matches reality. Okay. Now, so the idea is that renormalization describes how we get an effective description of a physical system starting with something more complex and complete, and then throwing away information. And then now we want to go the other way, which was this equation, and describe how, as we get more information, we, if you like, integrate in and increase our levels of accuracy of the model. Okay, so the upshot is that Bayesian statistical inference, the process of learning more about nature through observation, is regarded as the inverse to exact renormalization group flow. I'm just going to repeat those words a lot. So I've done the intro bit and told you that RG, well, it's that direction, and Bayes is going to be that direction, and now I'm going to try and put some equations behind these words. So ERG is somehow less used than the Wilsonian approach. Here, I should put Polchinski's name up here for sure. So Wenger 73, and then you've got Polchinski, whose emission is terrible, it should be there. And the 90s, Tim Morris, which is the approach we know now, 94. And then recently, we're following Cutler and Rezhnikov in a recent work where they brought out some of the approach that I'm describing now. And in that approach, what you do is, in order to do ERG, remember you've got this flow is determined by a functional. You write it like this, and the idea is that you basically, as you change degrees of freedom, you reparameterize fields, and this thing here is given by this functional, which is called the reparameterization kernel, which has all the information in of how you do the flow, and that's determined by two pieces of information. This thing called C dot, which is a regulated two-point function, and this thing sigma, which is a shifted action. So this S will be the usual action of your theory, and this thing, S hat, is actually, I think Cutler calls it a seed action, is actually like a reference point. And that's associated to the scheme choice. Everyone asks that question, Neil. And you can take the two away, and it corresponds to a different sort of scheme when you put this into equations. That choice with that two makes it look nicer, and you can land on equations that you recognize. But even why you need a reference action at all is a bit, it's like what you're doing is, and you'll see it a bit later, is you look at the functional being defined as a difference between two actions rather than an action in itself. And it's useful to put in an action rather than just zero. And then why there's a two is like a normalization choice. Okay. Okay, just some notation. S will be the manifold which has the reference measure. So that's the thing that you're going to integrate over to make probabilities 1. M will be the space of probability distribution. So this is a infinite dimensional space associated to the space of all probability distributions on S. Okay. We'll have a tangent space to M, so that's a deformation of a probability distribution which integrates to 0, because we want to consider deformations which still preserve probability. And I think the upshot, rather than going through all these details, is that the key point, after defining various things, is that you can write the equivalent of the heat equation for probability distributions, where we think of, this is the point, the Laplacian of the probability distribution viewed as a function on S, then the gradient of that, which is given by, somewhere I have it up there, is given by this. Okay, that's the energy functional. Okay, now a key point, which is very important, is if I have a space where I'm saying I'm going to construct a Laplacian on the space of probability distributions, then I need to know what the metric is, an appropriate metric on the space of probability distributions. So that metric is what goes by the name of the Wasserstein 2 metric, and this was introduced, well, it's been around for a long time by Wasserstein. It was introduced in this context by Villani for transport theory, and the Wasserstein 2 metric is a measure of the distance of how you turn one probability distribution into another, and the Wasserstein part might related to optimal transport, is that during the flow from one to another, you must always maintain normalization being 1. Okay? And so the key point is that with respect to the Wasserstein 2 metric, the gradient of the differential entropy in the system is equal to the Laplacian of P. So then this is the Laplacian of P, that's the gradient, and then you can introduce an additional potential function, And then you can obtain what is called the Fokker-Planck equation, which tells you how the flow of a probability distribution has a natural term in terms of this gradient of P, which is essentially an entropy-given flow. And then if you've got some potential, then you add some additional term. Okay, so this is Fokker-Planck. Okay. Right, so to bring this together, given a normalized probability distribution like this, gradient flow with respect to this turns out to be related to the KL divergence. Okay, so the KL divergence, going back, is the thing that was sourcing the Bayesian flow, and then you can rewrite that in terms of this f of p and write the same thing then as the Wasserstein gradient of the KL divergence. So all we've done after lots of flicking about with Fokker-Planck equations is rewrite that Bayesian flow in probabilities in terms of a flow in a space where the space is the space of probability distributions equipped with a Wasserstein 2 metric. And this is what you get. Okay. Now, what you can then do is realize the Wenger-Morris equation for exact renormalization group in the same way. And in particular, these two different probability distributions, this is related to Neil's question, are these difference of actions. The 2-point function in Wenger-Morris is the inverse metric on that probability distribution space, which was related to the Wasserstein 2. And then you compute, and then you show that the flow of probability distributions is given by this thing, which is the finite version of Wenger-Morris. So the exact renormalization group flow, you can again see as a flow on the space of probability distributions dictated by this sort of diffusion equation with this potential. Okay? Right. Okay, so this is meant to be a summary of what's happened so far. Exact renormalization group you can see as a convection diffusion equation in the space of probabilities. The two pieces of data that determine what that flow is have a, I said, clear interpretation. One is a 2-point function, and that 2-point function corresponds to the inverse metric on the space of probabilities, and the functional sigma is a sort of distance between probability distributions. Okay? Right. Any questions so far? No. Good. Right. So we've done that. I'm not going to go, I don't want to go through the whole technical thing of how this links to stochastic differential equations. But there is a whole story that once you've got something like a probability distribution, you can link this in a differential equation associated to a probability distribution. You can link this to stochastic differential equation and stochastic processes, and essentially link Fokker-Planck to these sorts of differential equations. And then these differential equations are the way in which you see that you get ordinary diffusive operators that you're familiar with. So I won't go through that, just hint at it. But basically, you're all familiar with these sorts of equations, and then solving it with a heat kernel method. Once you've got a heat kernel method, you've then got a transition operator, which tells you how with the probability for going between states in a time t. So this is often what we use in quantum mechanics. But yeah, I don't want to go into too much into that. That's the stepping stone. The key point now is that was Wenger-Morris was written in this form, is to go back and look at Bayes. So I'm going to describe what's called the Bayesian inversion problem. So Bayesian inversion is the following thing. We have two sample spaces of random variables y and u. We assume there is a process where we've got a signal u is mapped onto an output. So y is the output, u is the input in some way, and there could be some function, and then n is noise. So this is often what actually really happens in nature, that nature's trying to tell us something y with a signal u, it goes through some box g, but then there is noise in the way. And so the inversion problem is that what you want to do is, given y, determine what u is, given the fact that you've got noise on the way and some processing of u. Now, because of the presence of noise, you can't for certain know what u is, because even if the function g is invertible, because of random noise that's coming when you measure stuff, you can't do it. So the inversion is when you come up with a probability distribution over u, and you only have a probability distribution because of the presence of noise in the stochastic process. Okay. Right. So this is the idea of Bayesian inversion, and is a relatively recent approach, and this is an approach used in signal processing and quantum information. So let's go through this. We postulate for you a prior measure, which is what you think the probability distribution of u will be. We treat n as a random variable, which will be independent of y and governed by its own probability distribution. Then we get this allows us to then define a conditional random variable with y given u, like this, and then you have what's called an information theory channel, which is a map from the output given this way to noise, and which then gives you a conditional measure given by this. So this is the output, which is then saying the probability of y given u is given by this. Okay. Now, suppose y is a set of t, that's IID random variables. IID is independent identical random variables. What's the D stand for? Independent identical distribution, thank you. Random variables drawn from the data generating that. So basically all it says is that what determines the data is the probability model. The data that you pick is not determined by the data anywhere else. And this was our equation, which was from Bayes, about how this probability distribution changes as we observe that data. And then we assume the data generating distribution can be realized in the form of this conditional density. So this is just this thing of saying that the real data can be written as a form in the same model. And then one of the things that we showed in the first paper is that sufficiently large data, the two endpoint functions of the t posterior can be written like this. So this is an analytic result, and it basically says the expectation value for two endpoints you can write like this, and the key point is this thing here, which is that this is the inverse of the Fisher metric for the family of probability distributions. So what this says is that you can look at the two endpoint functions, and the expectation value where you've got data amount t is given by this thing, which allows you to extract out the Fisher information metric. So for those of you who don't know, the Fisher information metric is how we do information geometry. It's a measure of distances in terms of information space, and was introduced by Fisher, and it's essentially it's the second derivative of the KL divergence. Okay, so the appearance of this thing in this expectation value is where we have the entry of information geometry into the endpoint theory that you're measuring. Okay. Now, This has all been very abstract, so I'm going to try and give an example that's a real concrete example. And it's going to be where we have a Gaussian distribution, and the noise will be also drawn from Gaussian noise with variance sigma squared. Okay? So I want to learn what mu is, but I'm going to get a whole bunch of noise on the top of it, where the noise is given by sigma squared. Okay? So this is a typical thing that you want to do. And then if you solve the equations that we've just written down for you, then what you'll get is the posterior probability of mu, the thing you want to measure, given the observations of y that you see, subject to the noise n, will be given by this thing. Okay. So obviously, as you get more data and t goes to infinity, this collapses to a delta function, which is what you want, where mu is equal to mu star, the true value. So this is a first step of sanity, that if you have an infinite amount of data, your probability distribution will collapse to a delta function around the true value. But it also tells you something else. It tells you how fast you need to go compared to the noise that's interfering, because you want t to go much bigger than sigma squared, and you can see that you get the scaling with like square root of t, and so on and so forth. Okay, so this tells you how much more data you need to get in order to get a better estimate of what the thing is that you're trying to measure. Now, if you take the inverse time, so t remembers the amount of data, if I just define tau, like so, obviously you put that in, you get this. And then this you recognize as the solution of the heat equation. So, then the posterior distribution is that in inverse time, in inverse the amount of data, is the same as the standard solution to the diffusion equation with diffusivity sigma squared. What that means is that you what you're doing is a sort of Bayesian diffusion. It's like diffusion running backwards when you do Bayesian inference, with tau goes to 1 over tau. So it's an inverse process. It's not the reverse process. That'd be t goes to minus t. This is t goes to 1 over t. And of course, sigma squared is what sets the scale for the process, which is the amount of noise. Okay, right. So this is a set of experiments showing how this really works. This was for the Ising model. And what you do is you take the Ising model and then you measure a whole bunch of configurations of spins. And then from measuring the configurations of spins, you infer what the coupling is in the Ising model. Okay. And when you do that, as you take more and more data, so this is the number of samples of configurations of the Ising model, you will zoom in onto, and this forward scale here is j, you'll zoom in onto the true value of j. But you do so through, this is repeated again and again. If you just do it once, as you increase all the things, you get some path, and it's a stochastic flow. And just from one path, it looks very unpredictable. When you take all of the paths, you just repeat this again and again and again, you then get this probability distribution, which is this thing here. So it's only when you sum over all paths of gathering possible data that you then get this distribution, because you're looking at the probability distribution of what you're inferring. Okay, so it's not enough to do a set of measurements, you've got to do the ensemble of set of measurements, and that's what you're doing the probability distribution on. Okay. Right, so this then describes what's just gone on, and it's, rather than go through these equations, if I point to this thing, what this is, so these is 20,000, say, to 100,000 measurements. Now, when you're at the end, you should infer the same thing. because the total set of measurements is the same, and it shouldn't matter which order you've taken them in. But while you're taking them, there's a whole load of different ways in which those measurements could have come about. So what happens is, just by acting on the permutation group of all of the ways in which you could change the order of measuring things, you will get this sum over paths. Okay? So it's a peculiar way in which the sum over paths appears when you're doing this ensemble of measurements, is you will get this sort of path integral approach. Okay? But then in the end, you always end up at the same conclusion. Okay. So thus we see the trajectory of the maximal posterior estimate is determined entirely by the sequence in which the data is observed. The posterior estimate is the final thing. The terminal distribution is invariant under permutations. And then, but how you get there and is very much open to just a random ordering of observations, and that this is related to the scheme question in ERG. Right. I don't want to go too much into this. Okay, so let's go and extract more detail in terms of the posterior distribution in Bayes. So this is just using the Bayes formula for the probability of a variable y. This is the posterior probability of your model, and then this is basically the probability of your model given the Bayesian inversion problem. And then you keep on going, and then you work through these details, and then what you'll end up with is a formula like this, which is a diffusion formula. And then from that, we can identify that the term that appears in front of the second order term, which is Kij, is the Fisher information metric. So pullback of the Fisher information metric, which measures the information that we have. Okay. So I think we'll go on the summary. I'm aware there's a lot of details, and we're not all in love with statistics here, but let me give you the upshot. In ERG, the time parameter t is really log lambda. It's the log of the scale. In Bayesian diffusion, that would be the data will be tau, and they're related by being inverses. In ERG, the inverse metric Gij is related to the two-point function regularized, and that's related to the inverse Fisher metric, which is the metric on information space. The potential function in ERG is related to the log likelihood function in Bayesian, and the scheme, which is defined by this difference of actions, is related to this log likelihood ratio. Okay? So what this does is show that there's a dictionary that allows one to translate between renormalization group flow and the diffusion process with a backward process in Bayesian inference. Okay, so we can invert a renormalization group and flow to the UV in some sense. Okay, so let's discuss scale. So in field theory, the context role of the inverse metric was played by the two-point function. And now in this backwards diffusion process, it's really the Fisher metric. So it's like the Fisher information is what gives you the scale on the space of data. Because normally when we talk about renormalization, there's this notion of a scale, and you could say, well, if I just give you an arbitrary list of data, what's the equivalent thing of scale? So the answer to that is that's given by the Fisher information metric. Now, the next question you could ask is, in Wilsonian RG, there's the whole question of renormalizability, non-renormalizability, marginal operators, conformal field theories. And then you could ask, in the language of statistical inference, what do all these things correspond to, like being a conformal field theory? Okay. So a conformal field theory is determined and completely defined by its two-point function and three-point function. In statistical inference, that would be saying that you have a model where you only need the 2-point and 3-point correlators to determine the whole model. It's very usual we have a model in the infrared, as we would say, which is a Gaussian model in statistical inference, because that's a theorem that when we have large amounts of data, then we end up with a Gaussian model being sufficient for the space of estimators. So now this sort of seems to indicate, unless one thinks very carefully, when we do statistical inference, we're always flowing to some trivial infrared theory. Okay. But then one could try and do something a bit cleverer because of this, and then construct probability distributions which are specified with only a finite number of connected moments. Okay? So this is new. Statisticians tend to use either infinity or 2-point functions, nothing in between. And one of the opening things about this is whether we could have probability distributions that flow under obtaining data that have more than the Gaussian theory, but not an arbitrary number of infinite moments. I won't discuss quantum error correction. I will discuss diffusion learning. So all of this seems very abstract and useless. Let me say how actually this sort of thing is really used. So I just Googled DALI images. So DALI 2 came out, I think, the beginning of last year, and is a mechanism for generating images where you put in a prompt, and then it creates an image for you. Okay? And here are some examples. You know, you just say something like astronaut on a white horse, and it will produce that for you. You say something in the style of DALI, it will produce that, etc. And you can go and play. It's on, just Google DALI 2, and then put in a prompt, and it will generate these images. So the question is, how does it generate these images? What is the coding that this thing uses to do that? So it's taken from the web all the images on the web. Perhaps not all, but a large data set. That data set has a hugely complex probability distribution. So what people did is what's called diffusion learning, which is, I'll go back to the talk. Yeah. So what diffusion learning is you take some intractable distribution, well, that's the distribution of all images on the web. And what you do is you start from that data and you flow through a diffusion process so that for each point of an image, you do a flow, which is diffusive, which then maps you to a Gaussian. Yes, Neil? Right, okay, good. So one of the things that really I've learned in dealing with AI is that everything you learn is a probability distribution. So when you say of what, it's basically, you look at the number of pixels, and then you've got red, green, blue to some intensity, and then there's a probability distribution over that multivariate space. Pixel 532,42, red, what's the probability that's on, let's say, or intensity 5, that's a probability. So if I've got, so in other words, I've got the space of all images, let's make them the same size, and then you've got what you want to do is look at the probability that each one of those pixels, it's a large multi-dimensional probability distribution where you should think of the variables are the location of each pixel in red, green, blue. And then yes, an average is not the word you should use. The images on the internet are samples from that distribution. And what you want to do is learn the distribution from the sample space. So the idea being that if you know the distribution, you can then resample from it, which will then produce a new image that will look like an image, because what you as a human know is secretly the probability distribution of images, and what you tell when something is wrong is it is an outlier. And you go, that doesn't look right. Okay. It's the same with voice, it's the same with image, it's the same with any piece of data. It's a probability distribution. What you as a human has done is effectively modeled that distribution so you can tell when it's not right because you know what the distribution is. So it seems anomalous, and then that's what you get nervous about when you see something done by a bad computer. Or it's the same if we got a chat. You know, you've got some annoying chat bot, and you can tell it's a chat bot because it's not replying how a human would. That's because there is a probability distribution on the space of things, okay? So it's exactly that Bayesian problem. You want to learn a probability distribution that's multidimensional and huge, and you've just got instances of it, samples. So of course the first thing is you need many samples to get anywhere. Fortunately, we've got the internet, which has got many samples of images. You learn them all, you sort of do Bayes, and infer a probability distribution, but it's very hard to do in practice. So what people did was this: to learn the probability distribution, you run a forward diffusion process from each sample point, and so that you know you will map down into what we would call a trivial infrared theory, which is a Gaussian distribution. So you learn a map from an arbitrary probability distribution to a trivial distribution. And if you learn the map, that means you learned the distribution, because you can then start with the Gaussian distribution and run it the other way, map the inverse. So remember, the fact this is invertible is crucial. So that's what people did. They took all those samples, they learned how to map the sample to the Gaussian distribution, and then to generate those images, you give it a draw from a Gaussian distribution and run the inverse diffusion process as described by these equations. And you'll generate those images. So the insane thing is that those images are ridiculously realistic. You can, if you've not played with DALL-E 2, try and say things like photorealism, and it will produce something that you will not be able to distinguish from a photo. So really what we're using is exactly what's in here, is you're sort of doing renormalization flow into a trivial theory, but then using the inversion of the flow process to go into the ultraviolet and generate an instance. And that's what we do when we're doing things like generative AI. See, everyone woke up when I showed pictures. More pictures. There is this correspondence between ERG and dynamical Bayes. There's all sorts of possible applications in understanding things like monoticity theorems, just in the quantum field theory approach. My collaborator is very much interested in bulk reconstruction and holography, because renormalization is a key part of holography, and any understanding of that is quite useful. So this gives a sort of information theoretic approach to what we do when we're flowing in ADS. I mean, I like putting these sort of trivial pieces of trivia out there. I mentioned the Fisher information. One of the pieces of information that was around for a long time is that if you have Gaussians, the Fisher information on the space of Gaussians is ADS space, which is a rather peculiar thing. And that flow sort of driving you a way where you shrink the distance is like a flow to the boundary of ADS. So there's already in information theory a natural ADS that appears even in the free theory. And then you can sort of go backwards and forwards. As I said, there's a very interesting thing of looking at this sort of flow that they did with Dali was just flowing to what we call a trivial infrared fixed point to a Gaussian theory, but you might decide that there is something very crucial you want to preserve in the three-point function, say, and then this will tell you how to do it. You could come up with generative flows that would preserve correlators that you could choose. And that's of interest to all sorts of people who want to use generative algorithms for things other than art, because you want to preserve some things which you say and know are important. Oh, yeah, I'll leave it there. Okay, thank you very much.
Questions for David? Yankui?
Just out of do curvature singular solutions to the Fisher metric mean anything?
When you say, well, you mean really like a 1 over R type singularity or something?
Oh yeah, or just is there a Fisher black hole?
Oh, yeah, I've tried that. Lots of people try that. So everything I did was Euclidean, and the Fisher information is always Euclidean. If you come up with an idea of how to make the Fisher information Lorentzian, you tell me first, because that's an interesting thing.
And for Euclidean singularities?
For Euclidean singularities, I think you can have them. You'd probably have a natural cutoff somewhere, because there's a sort of integral in defining the metric, because it's like an integral of the p log p over q. So, because if you've got a finite number of degrees of freedom in your theory, the Fisher information will probably be finite, but there's some smooth limit, right? So it would look like it was going to a singularity, but you'd probably always have a cutoff given by just the finite number of degrees of freedom in the theory. But there's no Lorentzian thing, which is interesting. Oh, no, I mean, you get things like that. I mean, that just means, you get things like that all the time. So, you know, if I've got two pieces of information, those pieces of information can be very far apart in some instances, and in some instances close together. So, because what you're doing with Fisher is, you know, it's related to the importance of the information. So the fact that, you know, Ronaldo's rather upset at United, and I don't know, some other Portuguese players upset somewhere else before the World Cup doesn't mean much. When they all come together in the World Cup, it means a lot for Portugal. That sounds a bit stupid, but what it's saying is just that change in metric is that pieces of information have different correlations and importances depending on other bits of where they are in information space. So that's not, you know, that is what you expect.
So conceptually, I mean, you're looking at the renormalization group flow, which is a physics concept. Now you're mapping it to a math concept, which is probability theory. Is the hope that hopefully you can use some of the founded math already, translate back through your dictionary and come up with physics results?
I mean, it would be nice to be able to say something more about renormalization group theory, but I think that has been better understood and well studied in physics. And I don't know, I mean, I think its use in the physics thing will be more about in terms of ADS and this whole thing which they call bulk reconstruction, because it's a way of sort of using an information theoretic approach to say what you're doing as you're going in. Where there is, if you like, a gap is much more in the sort of things that we've done and understood in quantum field theory to do things like diffusion. Diffusion was the most simple way of doing this. This thing about preserving endpoint functions as you flow, which is the sort of thing you all know about in a conformal field theory, that you have a non-trivial three-point function, is something that has not been used yet in statistics, ever. So if you like, all of statistics with a central limit theorem is built around trivial infrared fixed points. Coming along and telling them, like the phi brane, you can have a non-trivial non-trivial infrared conformal field theory, says I can take data and data and data, I'll break central limit theorem, and you'll still have non-trivial three-point data, and that will be something that you can do. That's a new notion of statistics.
I see. Very interesting. Should we ask you about quantum error correction now or later?
No.
Later. Okay, great. Let's thank David for the very nice talk.
Thank you.